Okay, welcome to EGR445, and in today's class I'm going to extend the discussion. I'm going to discuss the coupling design. In the last class we actually looked at the coupling design for MUF or simple sleeve coupling. In today's class I'm going to extend that approach to design something called as the flange coupling. So what is a flange coupling? So flange coupling. Now the coupling that we saw in last class, it was a sleeve coupling. The issue with the sleeve coupling is it cannot transmit large torques. Even though the shaft may be good, designed from the torsion point of view, but unfortunately the coupling, since it's sort of a hollow coupling, may or may not work. So many a times what they do is they add flanges. So how do these flanges look like? So you have a shaft. This is the center line of the shaft. Then there is a keyway. Then there is the hub. This hub has some sort of a flange. Flange is an extended portion. And on the right hand side, you are going to have the other shaft. So you would have the other shaft. And the keys are usually perpendicular to each other. And then you're going to have another flange. Then it would be like this. So in the case of sleeve coupling, you just have one pipe going from the input side to the output side. In the case of a flange coupling, what you have is you have a flange, and then these two flanges are sort of bolted together. So you have bolts here. There are some variations to this flange coupling, and those variations are to account for slight misalignment. You could add some sort of rubber bushing. So what they do is they usually add some sort of rubber bushing, and the purpose of this rubber bushing, so this is the shaft, this is the output shaft. This is the input shaft. This is the flange. Then key. You have this bolt. And you could have this bush. Now, the purpose of the bushing is to allow slight deformation, and that deformation would actually compensate for any misalignment. It could be angular, or it could be sort of eccentricity or displacement misalignment, and still the coupling would be able to function. So what would happen is the shafts would run concentric, and the eccentricity or the offset would be compensated by the deformation of the bush. Now, how do we design? The design process for a flange coupling is exactly similar to the uh, sleeve coupling. So what I'm going to do is I'm going to give you the step-by-step design recipe for design of flange coupling. So what are the elements that we need to design? First and foremost, we would be given power to be transmitted in kilowatts. We would be given speed in RPM. Sometimes they would give us factor of safety or overload factor. So you would get some sort of KF, which is the factor. And from these, we should be able to find out the value of torque. And once we find the value of torque, they would specify the material for the shaft, material for the flange, material for the key. Usually the flange is made up with cast iron. So you can have this made up with cast iron. The shaft would be typically a steel shaft. It would be a steel shaft. So step one is design shaft. And after you design the shaft, remember, we need to design the key, or you would update or modify the shaft, modify shaft for key weakening. Step two is design key. And once you design the key, you need to find out the width, thickness, and length of the key, the same design principles that we talked about. Then step three, this is new, is we have to find out the number of bolts and there are some design guidelines for number of bolts. Usually you will not have odd number of bolts. You will have typically even number of bolts. So as you can see, if you have a flange coupling and if you have a shaft that is attached to the flange coupling, just for symmetry, it would be easier, and for balancing, it would be easier to have 4 bolts, 6 bolts, or 8 bolts. So at minimum, you should use 4 bolts. But if the shaft diameter is greater than 55 millimeters, so if D shaft is greater than 55 millimeter, then you can go with number of bolts is equal to 6. If the shaft diameter is greater than 150, then you can use N is equal to 8. So that is how you would find the number of bolts. The next step, and I will give you detailed guidelines. That next step here is to find the bolt diameter. So how would you find out the bolt diameter? So when we design the bolt, we have to make sure that the bolt is able to withstand the torsional stresses that are induced on the bolt. But what I want to show you here is, if you look at the 3-dimensional view of the flange coupling, if you look at the 3-dimensional view of flange coupling, you are going to see something like this. So you would have one flange, you would have other flange, other side hub, and you're going to have the shaft that is going out. And you're going to have a bolt here, you're going to have a bolt here, you're going to have a bolt here, and one bolt and the back. So think about it, that you have the torque which is acting on this input shaft. The same torque get transmitted onto the output shaft via the flange coupling. So what it means is there is a force. There is a force that is perpendicular to the radius at which the bolts are circled. So basically, this is the R bolt. So you need to find out what is the magnitude of that force. And that to find that force, what we do is, if we consider the pitch circle diameter of the bolt. So if this is the PCD, or pitch circle dia, PCD of this bolt, then what we do is we can find the value of, we can equate torque is equal to F multiplied by PCD divided by 2, and that would give me the total force on the bolt. So this will be F total. And this F total would be the number of bolts multiplied by force in each bolt. So once I found out the force in each bolt, please understand, even though the coupling is transmitting torsional power, or is transmitting torque, the loading on the bolt is force, and that would actually cause that bolt to shear. So if we want to design the bolt to find the bolt diameter, tau is equal to F bolt divided by pi by 4 dc square. And one thing I want to tell you about the bolts, if you look at the way the bolts are made, or just think about screw, what they have is, they have an outer diameter and they have core diameter. So if you think about it, it's going to be something like this. So you have outer diameter and you have the core diameter. So this is D out, DO, and you're going to have something called as the inner diameter, which is the DC. Now the bolt is weakest at DC because that is the minimum area that has to sustain the external force. So what we do is, please note, we find this minimum area. So we use this DC to find out the core diameter of the bolt. But when you look at the data sheet, or when you look at a catalog, and if you go to McMaster-Carr, or if you go to some other online vendor, bolts are specified by their metric units. So it would be M10, M5, M12. So that indicates the nominal diameter of the bolt, which is in between core diameter and outside diameter. So this would be something called as the nominal diameter, DN. So if you have an M10 bolt, that means the nominal diameter of the bolt is 10 millimeters. And depending upon the specifications of the screw and specification of the nut, there could be some different tolerances. So you actually specify the geometric and other tolerances, just to make sure that when you pick up an M10 bolt and assemble it with M10 nut, they actually assemble properly. Now, I want to talk about this proper assembly concept for just a minute. When do you think a bolted joint is good enough? So for an example, if you want to assemble two plates, or you want to assemble this flange coupling, okay? And you get this bolt and you get this nut. So you are going to have a bolt on the left hand side, nut on the right hand side. How many turns they should engage so that you can comfortably feel that the joint is secured? If you observe a nut or if you observe a bolt, the first thread is never complete. It's always an incomplete thread. So that thread does not have any strength. So if you decide to make an assembly with just one thread in engagement, that is not the safest way to do it. Second thread is basically sort of aligning the whole helix. And once you start from the third thread, that is where you are going to have the full contact, and that is when your design calculations are going to be valid. So wherever you are going to assemble nut and bolt, you got to make sure that minimum 2 threads are coming out of the nut. Partial engagement is very dangerous. Then the other question is, how many full threads should be in contact for secure joint? So you have a nut, you have a bolt, and then how many minimum number of turns the nut should have for a complete assembly, or the assembly that you want the joint to sustain. Whenever you assemble, please try to understand it actually is dependent on the type of joint that you desire. For example, if you are looking at just a joining operation, no watertight or no oil tight or no airtight, then probably minimum 3 number of turns in contact is okay. So if you have assembly, something like a flange coupling that you want to assemble, 3 turns should be in complete contact. So your nut must have minimum 3 turns to engage with the bolt. But depending upon the application, that could change. For an example, if this flange coupling is operating in an environment full of dust, oil, or debris, then in that case, you want to include, just for safety, make sure that there are more turns. Now here comes a question that you have to work with what you have, but you want that joint to be secured, and you don't know like what environment that's gonna get operated into. So what you can do is you can use some sort of locking fastener, or basically some sort of sealant between the nut and the bolt that will ensure the proper contact and uniform distribution of stress. And depending upon the level of strength that you want, there are grades of sealers that you can use. If you want to make it a fully permanent assembly, you can use something like a Loctite. And there is a higher grade too, that once you add that, that assembly is not coming away. You cannot take it apart. There is another important point I want to discuss here. Imagine if this coupling is operating in a very high temperature area. Classic example. If you have a rear wheel drive, typically you have some sort of a universal joint that goes from the front of the vehicle engine all the way to the back of the vehicle. The engine, if you have a flange coupling somewhere there, then that's gonna get very hot because it's very close to the engine. So in that particular case, you want to add some sort of high tensile or high temperature lubricant that will maintain that those threads don't sort of get hot welded. Otherwise, what may happen is those threads on the bolt and the nut, basically at the end of the operation, after running that for 5-10 years, the whole thing would become solid, whole thing will get welded. That's why you want to add some sort of a lubricant or high temperature. They don't call it a grease, but it's a sealant. It's basically, it makes sure that these two dissimilar materials, they don't get some sort of chemically deformed or thermally deformed, and they become one single piece. So these are small things So once you start working with the actual assemblies, or once you start working with actual machines, you will observe. Now, next point, which I want to talk about is there is design of hub. So as you can see, this is the outside diameter of the hub. So this is DH. And if you were to neglect the part of the flange, if you were to neglect the top part of the flange, you would observe that this sort of becomes a sleeve. So what you can do is you can treat this as a sleeve design. So these are the important points in design. And now what I'm going to do is I'm going to give you a step-by-step recipe to find out all these dimensions. And at the end of the design, we should actually draw a neat sketch and kind of show all these important dimensions. But please note, this entire design is dependent on torsional stresses, and the equation is T divided by J is equal to tau divided by R. So any questions before I start solving?
Yeah, I have a question.
Yeah.
So we're calculating the force based on the diameter of the screw or the bolts. Does the friction between the two sections not take into any account? Are we just building it so the bolts are seeing the entire
Yeah,
shear force?
flange is not supposed to take any stress. So basically there is no, you can't assume that there is some friction that is in between these two. And typically the flanges are very well machined. So you will have some sort of surface finish specifications. So those the bolts are the load bearing members in the assembly. Flange is the structural component that is going to make sure that the bolt will stay where they are, bolt doesn't lose, and maybe provide some sort of tolerances or some sort of give for eccentricities or offsets. So no friction between the flanges. Everyone, any other question? Okay. So what I'm going to do is I'm going to step 1. Design of shaft. I'm not going to repeat the process. It's exactly same process that we discussed before, but I will write it down. So power is equal to 2 pi nt. From here, you would find the value of torque in Newton meter. If they give you some sort of overload factor, then TA, which is actual torque, is K times T, and your design would be based on TA. So TA divided by J is equal to tau divided by R. TA is the torque, J is pi d raised to 4 by 32, and R is equal to d by 2. So once you have these two dimensions, you should be able to find out the value of diameter from this equation 1. Then you have to compensate for key weakening. To compensate for key weakening, you would oversize the shaft. dA is equal to say 1.1 times d. Step 2, and by now you should know, is design of key. And there are 3 important dimensions: length of the key, width of the key, and thickness of the key. Can someone tell me the equations real quick for the key design? So step one is we need to find out the force on the key. So force is equal to TA divided by dA by 2. Then you can actually look at the crushing of key. And when you look at crushing of key, sigma C is equal to F divided by W by 2 multiplied by L. And the associated equation is shearing of key and tau is equal to F divided by L multiplied by thickness. And with this, you should be able to find out these 3 dimensions as a design guideline. If you are going to use a square key, then I'll just write this down. For square key, W is equal to T is equal to D by 4. I usually go with square keys. For rectangular keys, you can have dimensions D by 4 and D by 6. Next step, step 3. Now this step is similar to the muff coupling or the sleeve coupling. The only difference here is in the sleeve coupling, we did not have the flange. So now what we have is we have the flange. So what we have here is we have this flange. And there is a shaft. So this is the diameter of the hub. I'm going to call this DH. You have this diameter of the shaft, which is DA. Please understand, diameter of the hub, diameter of the shaft, you will have to design based on the torsional considerations. So what you will do is tau is equal to T divided by J multiplied by R. And T you already know, which is T is TA. J will be considering that circular cross section, which is hollow circular cross section, pi by 32 dH to the power 4 minus dA to the power 4. And now the stresses you will be finding out at dH, so which is dH by 2. The only unknown in this equation is dH, so you should be able to find this answer. Now there is one slight variation to this process. Many a times, if you look at the design data book, they will have some standard proportions. And these proportions, they come from empirical data. So like people have designed these types of couplings for hundreds of years. And they have found out that if DH is equal to 2 times DA, this is sort of a safe guideline for say shaft diameters maybe less than 55. So it is okay to use this equation, find out DH. So as an example, say you find out that your DA is say 50 millimeters from previous calculation. Then you can do DH is equal to 100 millimeters. But you can't stop there. You have to check safety based on these 2 dimensions. So what you will do then is you'll find out the value of tau, but you would use these values, pi by 32, 100 to the power 4, 50 to the power 4, multiplied by 100 divided by 2, and make sure that this dimension, this value is less than the safe stress for the hub material. Everyone understood this? So once you have that, we need to find out the pitch circle diameter. And so pitch circle diameter. So I'll show you what that is over here. So you have this hub, you have this shaft, and then here you have this pitch circle diameter. And this is where the bolts are going to be. So you have one bolt over here. I'm assuming our dimensions are such that we have just 4 bolts. So this pitch circle diameter of the bolt is usually, I'm going to call this PCD. So this dimension is PCD. PCD is equal to 2 times D hub. So basically, this is 2 times D hub, or it could be anywhere between about 1.5 to 2 times D hub. So that depends upon what type of material you are using, what is the application, and so where is this? So what is the justification for this dimension? Now I want to talk about justification for this dimension, and many a times when you go through the design process, you will notice these types of dimensions. So I want you to think about from a practical point of view. Imagine that you have this coupling. And what you want to do is, you want to decide the PCD, or the pitch circle diameter of the bolt. Let me ask you this question, which means if you want to insert the bolt, you have to drill a hole. Is it safer to drill the hole here? No. You agree with me? It won't be safe. Is it safer to drill a hole over here? No, it will not be safe, because it will bite into the shaft dimension. Now, how far this hole should be from this inner hole? So basically, this is the shaft. So what should be the distance between these two, so that when you are actually drilling the hole, you are not causing any cracks to propagate, or when it's actually in operation, it's not leading to some sort of crack propagation or some sort of failure, premature failure. So in that case, if this is your DH, if this is your DH, you want to make sure that the distance from here to here is sufficient to accommodate. This is very important. Distance from here to here is sufficient to accommodate the hub outer radius plus bolt radius plus some clearance, so that you can actually easily drill the hole, and when you assemble it, that bolt is not going to interfere with hub dimensions. Everyone understood this? I will repeat this once again. So the idea is this dimension comes, this is an empirical dimension. This dimension came about because we have this hub which is inside. Then we want to drill the holes, but we don't want these holes very close to the hub, or we don't want these holes very close to the outer diameter, because that will not be safe. And at the same time, we want to make sure we have enough space to put appropriate size bolt through these two flanges. That's why you can have this dimension as 1.5 to 2 times DH. Once you have that, you can proceed to step 3, which is the bolt design. Assuming number of bolts is equal to 4, assuming number of bolts is equal to 4, you know the value of torque TA divided by the pitch circle diameter of the bolt, PCD by 2, torque divided by PCD by 2 is going to give you force, which is total. This total force is number of volts multiplied by pi by 4 multiplied by the core diameter of bolt multiplied by the failure stress for bolts. So which is the failure shear stress, or also called as the design stress. So with that, the only unknown here is the core diameter of the bolt. So you got the bolt. Now, the next important part that I want to talk about is how would you find out the flange thickness? So step 4 is flange thickness. Now, when I say flange thickness, what I mean by that is now have so how do I find out this thickness T? How do I find out this thickness T? So let me ask you, if this flange decides to fail, how would it fail? If this flange decides to fail, how would it fail? So it would fail via circumferential shear. So please note, this is what would happen. This shaft would torque the hub. Hub will try to torque the flange, but for some reason, flange doesn't move. Then what would happen is this flange would actually come out, something like this. Right? And this hub would stay as is. So there will be this circumferential shear that would cause this flange to failure. So for flange thickness, this circumferential area F is going to be torque divided by the hub diameter dH by 2, because that is the force which is acting on the hub. So this is force, I'm going to call this FH. FH. And this FH is equal to pi times diameter of the hub multiplied by T. This is the circumferential area that is going to fail multiplied by the shear stress of the hub. And in this equation, everything is known. The only unknown is value of T. Do you agree with me? Any questions, any concerns? Now, the next thing is, how do you find out this outside diameter of the hub? This outside diameter of the hub is typically 3 times or 2.5 to 3 times dH. So this outside diameter of the hub, outside diameter of the flange is usually 2.5 to 3 times diameter of the hub. And these are the most important dimensions that you would observe in a flange coupling. Now, depending upon which design book you follow, there might be 1 or 2 additional steps. So sometimes what they do is they check the hub for some additional shear. Sometimes what they do is they check the bolt for crushing. So let me just write that down here. So next step, step 5, check bolt for crushing. Now, why would the bolt crush? The bolt would crush. I want you to visualize this failure. That you have the left hand side of the flange, you have the right hand side of the flange, and what you have is you have a bolt that is going in between. Imagine the left hand side flange grabs the bolt. Left hand side flange grabs the bolt, but right hand side torques the bolt. So in other words, if you were to look at this particular area, and we already know that this dimension is T, and we know the diameter of the bolt is B or DC, then what's going to happen is that the force which is caused by the flange on the right hand side is going to sort of crush the bolt where it is. Please note, this failure is different than shearing of the bolt. So if you have a bolt, that bolt could shear. That is how we designed it. But there is a possibility. Did I miss any comment from online? Is that D? Yeah. So if this DC, so to check bolts for crushing, sigma C is equal to F divided by T multiplied by DC. And this F would be F per bolt. So you take the force on each bolt, divide that by T DC, and this has to be less than sigma C. Usually the bolts will be safe for crushing. Now, one thing I want to talk about, and this is the perfect segue from the stresses that we talked about, is I want you to understand the contact that is happening between the flange and the bolt. So I'm going to draw the view here. So what we have is this is the bolt, and this is the portion of the flange. Just showing a little bit exaggerated. So what you're observing is this bolt is coming in contact with this area, and the bolt is crushing. Everyone understood this? So the area that I have shown, is different than the actual area the bolt and the flange are coming in contact with. I do not know if you observe this subtlety, but I'll show you what I mean by that. So if I were to take the cross-section area of the bolt, I slice the bolt, this is the flange, you understand that this is the area. So basically this is the area. So this is the outer circumference, half of the circle multiplied by the thickness. So that is exactly how that failure is going to happen. However, for practical purposes, we are looking for projected area. So what we have is we are looking for projected area. And this concept of projected area is very important, because whenever you have two surfaces in contact, they are circular, there is not just single stress, there is a uniform stress distribution because of the circular nature of the contact. So what it means, and you're going to see this again and again, not only in bolts, but also in bearings. So if you think about it, like you have a bearing, And through this bearing, there is a shaft that goes through. There is a shaft. So there is a shaft. Now you understand that if there is some load on this shaft, that this load will be distributed on this circular area. So basically, this is the area that would be supporting that load. But if you look at the stress distribution, the stress distribution is not going to be rectangular. The stress distribution at this contact, if I were to draw the stress distribution, is always going to be something like this. So it will not be a uniform stress distribution, but it would be a curve or a parabolic stress distribution. And to compensate, to account for this parabolic variation of the stress distribution, on the safer side, we use the projected area. Because if we were to use the projected area, what are we trying to do? Projected area is less than the the circumferential area. That lower projected area gives me higher value of stress, and that approximates to the maximum stress that you would see here, sigma max, which is, say, F divided by projected area. So we, as engineers, we use this trick again and again. When we design the bearings, we do the same thing. When we design sliding contact surfaces, we use the same thing. So remember this, keep this in mind. There is another hint I want to give you. This is a practical design guideline. Whenever you have this type of construction, like you have an inner hole and you have an outer circle. So you have some sort of an annular area. So as you can see, this is a bearing. This bearing has a shaft. So it's a design practice to use this outside diameter. This is D outside. Should be equal to 2D inside. So if this is the inside diameter, then the outside diameter should be 2 times the inside diameter. And whether you observe this or not, this proportion is used in a lot of applications. If you don't believe me, look at the bicycle chain. So this is the link of the chain. You know that there is this hole, and then there is another link. This dimension would be minimum 2 times the inner hole. So D inside, this would be D outside, would be 2 times DI. And the reason for that is just to make sure that the stress distribution is uniform. And that allows, that we have found out of testing or lot of design, that if the outer dimension is 2 times the inner dimension, usually our design would be safe. Okay, everyone understood the flange coupling design? So if you see a problem on flange coupling design, please understand flange coupling design is based on the torsional stresses, and then the shear stresses and normal stresses that we talked about. What you have to do is you have to follow the recipe, plug the numbers, and at the end create a very nice proportionate sketch and a CAD model for the flange coupling. Can you do that? Okay. Any questions from my online students? Any questions from my online students? Okay, next type of stress that I want to talk about is principal stress. Now, principal stresses come into the picture when you have simultaneous action of normal and shear stresses. Of normal and shear stress. So sigma is called normal stress and tau is called as shear stress. There are two types of principal stresses. One is a major principal stress and other one is the minor principal stress. Remember that from the design and mechanics of material. In design, or when we are trying to design, we are focusing on the maximum principal stress because we want to make sure that the material that we have is able to withstand the maximum possible stress that is generated or that is induced in that material. So sigma max is equal to 1/2 sigma plus square root of sigma square plus 4 tau square. So usually there is plus and minus, but since we are going to look at just the maximum principal stress, so it's going to be 1/2 sigma plus square root of sigma square plus 4 tau square. And to verify if this equation is correct, please understand, substitute value of tau is equal to 0. Substitute value of tau is equal to 0. Then you will see that this becomes 2 sigma divided by multiplied by 1/2. That gives you sigma, which is the normal stress. What this equation implies is the normal stress is the principal stress when the shear stresses are 0. Does it make sense? Normal stresses. So in this equation, sigma max is equal to 1/2 the square root in the parentheses sigma plus square root of sigma square plus 4 tau square. If you substitute tau is equal to 0 in this equation, what you get is you get sigma max is equal to sigma. What that means is if the shear stresses are 0, the normal stress is the principal stress. And believe it or not, I remember that one time one of the students got asked this question when he was applying for a design position, and they asked like, hey, imagine that you have a component which is subjected to the normal stresses and shear stresses. How would you design? So if it's a ductile material like mild steel, let's say you will use principal stresses component or principal stress failures and design using the principal stress. Then basically the question got asked is what happens to the principal stress when the shear stress approaches 0? Then the answer to that question is when the shear stress is approaching 0, the principal stress approaches the normal stress. So remember that. So principal stress come in the picture when you have simultaneous action of normal and shear stresses. And I don't know if you have seen something like this. You have an element. On this element, you have some loading, which is normal loading. You have sigma, you have sigma. Right now, the principal stress is equal to the normal stress. Now, what I'm going to do is I'm going to add a torsional stress or torque that gives rise to the shear stress. One thing I want you to understand, that shear stress would never exist in isolation. So which means if you have a shear stress which is going towards left hand side, to balance that, you are going to have a shear stress going on the right hand side. Everyone understood this? Unfortunately, the element that I have shown here is not in equilibrium. Why? Because you have a normal stress which is pulling on left and right side. That cancels out. Shear stress, the forces, the shear stress, the top direction on the top of the element is cancelling the shear stress on the bottom of the element. But these two shear stresses are giving rise to counterclockwise couple. Which means if you do not want this element to rotate, if you do not want that element to rotate, there is a complementary shear stress that comes in the picture, which is going something like this. So a shear stress would never exist in isolation. So this is called as the axial stress and shear stress combined. This is single axis. One more variation to this problem is you can have a biaxial loading, wherein you have the stresses, normal stresses in x direction, normal stresses in y direction, and you can have a three-dimensional stresses condition, wherein you have the normal stresses in x, y, and z condition. And now understand, you got 6 faces, so you are going to have three pairs of shear stresses on each face and on each side. So solving those types of problem would require use of software tool like finite element analysis. Everyone understood this? Now, just for my own satisfaction, I would like to cover one more part, which is maximum shear stress. So if you have maximum shear stress, can someone tell me what is the equation for maximum shear stress? This is the maximum shear stress. And how do you know this equation is correct or incorrect? Substitute sigma is equal to 0. Substitute the normal stress is equal to 0. Can you see tau max is equal to tau? Which means when the normal stress is going to 0, the maximum shear stress is approaching the shear stress. Everyone understood this interpretation? Any questions here? Now, what I want to do is I want to take a look at shaft design when you have these combined loads. Because when we are going to design gears, when we are going to design pulleys, at that time, we are never going to have pure torsion. And think about it, the shaft itself will be never in pure torsion because shaft has some mass. Mass means weight. So as the shaft is torqued, there is a self-weight, the mass times the gravity is acting in the downward direction. What it means is that shaft is not purely torqued. It is loaded and torqued. So in something like that, you just can't design the shaft based on pure torsion. You have to use the maximum shear stress to find out the total load. And I'm going to take one example. This is the shaft design. Using maximum shear stress. So here is a problem. So we have a shaft that is supported between two bearings. We have a shaft that is supported between two bearings. And there is a pulley at the midspan. There is a pulley at the midspan. And this shaft is transmitting power, say 1 kilowatt, at say 1000 RPM. And there is this pulley. The weight of the pulley is 200 newtons. The weight of the pulley is 200 newtons. So what I want to do is, I want to find out the diameter of this shaft. So what you have is, you have a pulley, and that pulley, the weight of that pulley is 200 newtons. The shaft is transmitting power 1 kilowatt at 1000 RPM. How would you design this shaft? Have you seen this problem before? Combined loading somewhere? How would you do it? First and foremost, we have to draw something called as the shear force diagram and the bending moment diagram, so that we can find out the maximum bending moment. I don't know how you did that, but I'm gonna give you a very simple technique, which is called as follow the arrows. Can you see that this is at the midspan? So say this is 200 millimeters and this is 200 millimeters. Do you agree with me? So what would be the reaction at either side? It will be 100. Do you agree? How would I draw the shear force diagram? To draw the shear force diagram, go from left to right, follow the arrows. So to draw the shear force diagram, go 100, go straight, come down 200, go straight, go up 100. Bending moment is maximum when the shear force changes its direction. So the bending moment diagram, if I were to draw, everyone comfortable with the bending moment diagram? It will be 100 times 200. This would be like this. This bending moment is 100 times 200 Newton millimeter. So the maximum bending moment is equal to 100 times 200 Newton millimeter. Now I need to find out the value of torque. So power is equal to 2 pi nt divided by 60. Power is 1 times 10 to the power 3 is equal to 2 times pi times 1000 times t divided by 60. That gives me the value of t. Are you with me so far? Now, what I need to do is I need to find out sigma from equation Bm max divided by I multiplied by y. So Bm max is 100 times 200 divided by pi by 64 d to the power 4 multiplied by d by 2. And I got this equation for sigma. Are you with me? It's just going to be in terms of d. Everyone agrees? Then I'm going to find out the same equation for t. So tau is equal to t divided by j multiplied by r. T is whatever you get from here. So this guy, whatever you get would go over here. Divided by j is pi by 32 d to the power 4 times d by 2. So do you agree with me that now my sigma will be in terms of d, my tau would be in terms of d? Do you agree with me? Any questions from online students? So to find out the maximum shear stress, tau max, what I would do is I would actually do 1/2 sigma square plus 4 times tau square root. And when I do that, I just equate this equation to the design stress, tau design. And please note, the only unknown in this equation is D. This equation is in terms of D. Everyone understood this? Have you solved problem like this before? Have you solved problem like this before? No.
Yes.
Yes. You like this method?
I like to follow the arrow.
Yeah. Oh, so I'll give you something similar to the follow the arrow method for shaft design for principal stress. And that comes from logic. And here is the logic. Do you agree with me that the normal stresses and shear stresses are perpendicular to each other? You agree? In other words, the moment, bending moment and torque, they are perpendicular to each other. You agree with me? So can I find out a resultant torque equation, something like this? This is very important. And this is the method that I'm going to use. This works. I'm going to find out something called as TEQ, which is square root of m square plus t square. Why this is m square plus t square? Because I know for the fact that the bending moment is perpendicular to twisting moment, right? And once I find this out, I can use this equation TEQ divided by pi by 32 d to the power 4 d by 2 is equal to tau. This is the design value, design stress. And the only unknown here is D. Much easier, right? And if you don't believe me, you can actually plug in what the values that you got in this equation and you will see, you will get the same answer. Okay, I'm gonna stop here and have a good weekend, and I will see you next class. Yeah, light bulb went on or what?